So, welcome back, where we are talking about the production of calcium sulfate along with the production of your phosphoric acid. So, calcium sulfate we are getting from that particular reactor where we are handling the ore. So, it can be filtered off. So, calcium sulfate is separated out and the acid is then concentrated to about 56% of the actual P2O5, what is known as the corresponding anhydride of your phosphoric acid. So, concentration up to that point can be utilized using vacuum distillation. So, basically we have to remove this particular water molecules whatever there, such that we will get something as that particular phosphoric acid which is known in the market as the syrupy phosphoric acid or orthophosphoric acid, or we consider it as the syrupy phosphoric acid as its corresponding form as the ortho. So, orthophosphoric acid, which is basically a very heavy one and really highly concentrated one, and it can be considered as in terms of your P2O5, because the P2O5 which is also an anhydride form of your phosphoric acid, and that we will see also that how we can utilize this also is a very good desiccant, this P2O5. Whether we will be able to make P2O5 also from that phosphoric acid, that will also be an interesting area to understand. So, this concentrated phosphoric acid what we use, we can get up to 56% of this from the wet process. Then other process we will be considering over here is your thermal process, that means heating something which can be burnt away to give you the ultimately your phosphoric acid. So, thermal process, as the name tells you, that now we will be utilizing directly the phosphorus. So, the wet process was giving us something where we are utilizing your phosphate rock or apatite rock from the simple treatment of your sulfuric acid. But if we get the elemental phosphorus, that means white phosphorus or red phosphorus from the phosphate rock, what we can do, we can use that particular elemental phosphorus for making pure quality of phosphoric acid, not directly from your phosphate ore or the apatite. Now we can utilize via your elemental phosphorus. So, that particular industry will give us what we can give you, that particular production of phosphorus from the rock sample. So, phosphorus will be there, it will have some utilization. So, making phosphorus from the rock is also another industrial aspect. And along with that, that particular phosphorus can be utilized for making phosphoric acid. So, how we do that? Simply we can go for burning phosphorus with a plenty of O2, what we are getting from air, such that, as I just now told you, that we are in the process of making P2O5. So, in process of making this P2O5, in terms of this P2O5, if we can burn it, we will get the phosphorus pentoxide, which is a useful desiccant. Still now we use it for the laboratory purposes in the desiccators and all this, which can very nicely absorb water molecules. So, absorption of all these water molecules will be useful for getting this P2O5 as a useful desiccant. So, it is a very costly one also. So, if we burn it, that P4, which is one form is the solid form, but if we can take it in the liquid form. So, this one form has been taken as the liquid form. With that oxygen of air, we immediately get that phosphorus pentoxide as the gas. And that phosphorus pentoxide in the gaseous form is the typical reaction. The thermochemical reaction tells us, because all the thermodynamic parameters we can calculate out, the temperature required, the product conversion, and all these things can be found out from this. But from the inorganic chemistry point of view, what we see now, that the oxidation of these in excess air, not giving us any other intermediate oxidation state of phosphorus, because whenever we are talking about this phosphorus, you should also be considered the corresponding oxidation state. This is the highest possible oxidation state what we will be achieving over here is your +5 oxidation state. So, that +5 oxidation state what we will be getting is for your P2O5. So, that P2O5 can be now condensed from the gas as a solid one, and that solid one is available in the market in the bottle form also, is the white powdered solid. So that white powder solid, some industry is there, is devoted in making this P2O5 and selling it to the market. So what we do, we have to have some furnace for making this oxidation process of elemental phosphorus. So elemental phosphorus oxidation by O2 of the air will give us the P2O5, and that phosphorus now it can be liquid or it can be a powder also, since we are talking in terms of a liquid form of that P4. It is sprayed into the furnace and burnt in air at a very high temperature in the range of 1800 to 3000 K. You see, very high temperature is required for this particular conversion. So high temperature oxidation of phosphorus basically give us phosphorus pentoxide. So what we will do now, as I told you that this phosphorus pentoxide in a bottle form is as a laboratory reagent is available as a solid white powder. So that solid white powder can be obtained from the gaseous form of this P2O5, and it can be condensed as a white powder, and it can now go for the next step of reaction. That means how we make phosphoric acid from your phosphorus pentoxide. So since it is the anhydride of phosphoric acid, so we have to hydrate it. So that's why it is separately hydrated to phosphoric acid. That means in a controlled manner, if we add or if we spray water on P2O5, we will get the phosphoric acid. So when we put in a laboratory the typical phosphorus pentoxide in a desiccator to trap the extra water of some compound or some material, such that we keep everything in a dry form, because some of the typical reactions also we can do over phosphorus pentoxide, such that water can be eliminated from the compound itself. Some organic compound can be transformed. If we take out that water from that particular molecule to convert it to some other form, that A can be converted to B. But if we have some extra water molecule in some precipitate, suppose that you can have some ferric hydroxide precipitate which has been filtered over a filter paper and we want to dry it up. So on the filter paper which is in the conical flask, so we keep that particular moist ferric hydroxide over filter paper within the desiccator, and the desiccator is supported by, at the bottom we can have calcium chloride, fused calcium chloride, which is moderately checking the atmosphere, that means moisture free. But it is not so good to dry your ferric hydroxide in moist form which has been obtained by filtrations. For that purpose we have to add some secondary desiccant, which is your P2O5. So P2O5 will take the extra amount of water which has been trapped in your ferric hydroxide precipitate, such that after 1 day or after 20 hours we get that particular ferric hydroxide in the dried form, that means the water free form. And by that time, if you are a very good looker on the situation, what is happening around you in the laboratory, in the environment, everywhere, you should be watchful all the time. If we look at the corresponding fate of the P2O5, because the P2O5 we have taken on a petri dish or watch glass, which is a white powder, and immediately after putting that powder we keep it in the desiccator, and after that, after 1 day or 2 days, what we get? We get the dried compound in the desiccator which was there in a round bottom flask, in a beaker or in a conical flask. We get that this one is getting moistened. That means the moisture is passing from your ferric hydroxide precipitate to your P2O5, and that P2O5 is moistened, basically taking that particular water and is giving you some glassy material, some sticky glassy material. So as it is taking water, it is quickly converting it to a corresponding version which we told you, that is a syrupy one, is not a liquid one, is a syrupy one, is a very sticky one. So that sticky material is nothing but your corresponding syrupy phosphoric acid, but still it can have the ability to trap further moisture, because your all the P2O5 has not been converted, some amount, some percentage of P2O5 has been converted to your phosphoric acid. So remaining one is within that particular sticky material. So the passage of water or water abstraction capacity of that particular material is decaying. So, it is very slow for the next step of water abstraction, but still it can take the water. Finally, it is basically a typically glassy material when all the phosphorus pentoxide has been converted to your phosphoric acid. So, this is a very nice example, laboratory example, if you see only that how phosphorus pentoxide can be useful for the industrial purpose for making phosphoric acid. So, we get this one, and this particular phosphoric acid we can convert for some other phosphoric acid salts. So, what we see now that in all these cases we have that particular thing, what we have produced so far is your H3PO4. So, since it is acid like that of your typical acid base reaction, if it is reacting with one molecule of sodium hydroxide. So, molar ratio of reaction is 1:1 such that this particular acid is a tripotic acid H3PO4. So, one of the acidic proton will be converted to your corresponding sodium salt, that means O minus Na, OH will be converted to O minus Na. So, if we convert only one of that, we will be getting NaH2PO4. So, monosodium hydrogen phosphate we will be getting. Why we are seeing all these things? Why we are studying all these things? Because this can have now some non-fertilizer applications. So far we have seen that phosphorus or phosphorus-based compounds can be useful for fertilizer applications, but this can be useful for some other non-fertilizer applications. So, first thing what we can try is the corresponding sodium salt. We can have some other salts also like that of your ammonium salt. We can have the calcium salts also. So, large number of salts we can make, because the property wise all these salts are different depending upon your cationic form what you are getting from that particular phosphate salts. So, what we will be getting is the corresponding phosphoric acid salt. So, when the reaction is 1:2, we get the corresponding disodium hydrogen phosphate. When it is 1:3, we get trisodium phosphate, or typically the simple sodium phosphate, which is Na3PO4, where all the 3 protons of phosphoric acid has been removed, and we get a typical anionic form, that means the phosphate ions present in that particular compound along with the sodium ions. So, we consider it as the sodium phosphate in your hand. And now, what we can use these, why we are making these? We are making something which is different now, as we will be getting something, because if we have one phosphate in your hand and another phosphate in your hand, whether we will be able to condense it to get some diphosphate, or we can go for further to make some triphosphate or some cyclic phosphates. So, whether we will be able to get something like that of our silicate formation, that silicates we all know that the silicate can have the certain type of silicate structures what we get in our cement, on the silicate material, clay material, and all these things for getting those structures. So, silicate is tetrahedral SiO4 ion we can have. SiO4 4 minus in phosphate is also a tetrahedral center, and if that can be condensed to for some other condensation reaction, the first one what we can get it is that since this one from reaction of sodium hydroxide can also be substituted by sodium carbonate, where your product is also your carbon dioxide, and that carbon dioxide formation is also there, and that will be typically eliminated from the medium, and that will also give rise to the corresponding sodium salt of these compounds. So, heating this particular disodium salt as well as the monosodium salt. So, we are having 2 salts, one is the monosodium phosphate and another is the disodium phosphate. And in one case if we heat it to 245 degrees centigrade, in another case if we heat beyond that from 300 to 900, that means above 500 degrees centigrade, if we heat it, we will also get 2 types of salts. So, when it is monosodium, we will be getting something Na2H2P2O7, and when it is disodium, we will be getting Na4P2O7. But the basic unit is all same, that means we get a diphosphate unit. So, this diphosphate unit only difference is the corresponding protonation level on the oxygen atoms present with that particular network. In one case, we have still 2 hydrogen atoms attached to the oxygen of the phosphate groups, diphosphate groups. But in the second case, we don't have any such hydrogen atom attached to the phosphate groups or the diphosphate group. So these are the corresponding one for making these compounds. So it is possible to make the diphosphates starting from your phosphoric acid. So higher molecular weight sodium polyphosphates we can consider, because it is basically a polymerization reaction through attachment of one phosphate to the other. So higher molecular weight sodium polyphosphates are utilized where we utilize, because they have some very good application for this purpose. Because the first thing we should ask all the time, because this is basically a application process, because the industrial process we are talking about, why we should study this, why we should know the preparation process, because it is a preparative method, and not only in the laboratory scale, but it is in the large scale, so industrial scale. So industrial scale is also very important. So that industrial scale of production will tell us that this particular material should be useful for some useful purpose. So if we can have some process where the people are making, the dairy industry, the agricultural industry, they are making some processed cheeses. So cheese making is another industrial purpose, so an industrial process, but that should be stored to increase the shelf life, such that we can have in the market for 1 month or 2 months in a packet form. In packed form we can sell it. So we have to increase the shelf life such that it is not degrading, it is not decomposing, it is not decaying in time. Because the milk products are always susceptible for bacterial infections or growth of the different bacteria in it, and it is degrading very quickly, even for simple lactobacillus production over there, which basically decay all the milk product. So this particular one can function as a stabilizer. So this higher molecular weight, only the higher molecular weight species, not the only sodium salts, that means the sodium hydrogen phosphate, disodium hydrogen phosphate, or only sodium phosphates are not useful. You can go for the more complex one, that means the bi, tri, etc. As a stabilizer for processed cheeses. It can be a stabilizer or it can be a protector basically for condensed milk. The Frankfurters, from the name of the German Frankfurt city. So Frankfurters is also some food material, and as pigment suspension stabilizers. In all these cases what we see is basically they are stabilizers. They are stabilizing that particular condition, that particular food material. That means if we have a cheese is not getting degraded. If we have the condensed milk will remain as the condensed milk. It will not go for its fermentation or any other bacterial degradation. So it basically stabilizing. So it will basically inhibit the bacterial growth, the degrading thing, that means decomposition of this material. That will resist that particular bacterial growth in that particular milk material. And sometimes this can also be utilized for tanning of leather, because we all know that the chromate tanning is also useful. The potassium dichromate or potassium chromate is useful for utilization of the particular process in the leather industry, which is tanning of leather. Similarly, these pyrophosphates or the polyphosphates are also useful in the leather industry. So the leather industry people are also utilizing a huge amount of these phosphoric acid salts. So how it looks like, one such example I am giving over here is your monosodium, once we call it monosodium phosphate, or you can consider as sodium dihydrogen phosphate or NaH2PO4. How we make it industrially, it is prepared in a two-step process by treating calcium phosphate with sodium bisulfate. So it's a typical process where we are handling something, instead of getting it as your corresponding sodium salt, now we are handling something which is known as your calcium salt. So since when we are using sodium, we are getting a trisodium salt. When we are handling calcium, you can use directly with calcium hydroxide or calcium oxide. You can get it as CaHPO4. So it is calcium hydrogen phosphate. So calcium hydrogen phosphate, truly speaking, it is not calcium phosphate, because the other one where we have seen that the rock material is also known as calcium phosphate, where no hydrogen is present. So it is known as calcium hydrogen phosphate. So truly speaking, it is calcium hydrogen phosphate when react with another bisulfate salt, which is sodium bisulfate. So it is biphosphate salt and another one is the bisulfate salt. So reaction of bisulfate salt with the biphosphate salt giving you a sodium dihydrogen phosphate, because the transfer of this hydrogen basically is taking place from this bisulfate to this biphosphate space. That means this HPO4 2 minus will have the greater affinity for proton abstraction from HSO4 minus. So, it is a typical simple acid base reaction. What we can consider as, if we have HSO4 minus in our hand and HPO4 2 minus in our hand, and we can ask the very simple question that where the hydrogen or the proton transfer can take place. So, which one is functioning as the acid and which one is functioning as the base. So, one of the species will have the higher affinity for the protons, that is why your HPO4 2 minus is functioning as a base. That HPO4 2 minus is abstracting the proton not from any other acid, but is taking that particular proton from a bisalt, which is your sodium bisulfate. And it looks like this particular dihydrogen phosphate, sodium dihydrogen phosphate is again another white, but is the granulous one, white granules of this material. So, why these acid materials we are studying? So, is a very huge subject of study. So, we can consider it in a large amount, and we will bet a little bit we will see also for your ammonium salts as well as some of the what we have seen like that of your calcium salt. So, it can also further utilize, because we have started our journey from your use as the fertilizer, then we are reaching over here for the leather industry. Now, we are going to some metallurgical industry, which is for metal cleaning. The technique for that particular metal cleaning, that the surface cleaning, metal surface cleaning is known as the phosphatizing. So, phosphatizing, that means the very small layer or a very thin layer of the metallic surface can be utilized for making the phosphates, and that phosphate, the metal phosphate can be removed from that particular surface such that you get a very clean material for electronic use or other use, where you use very clean and very neat metallic surface. So, these salts are utilizing for phosphatizing the metallic surface. Then if we have some the boiler water treatment, so that boiler water treatment also, that the water quality is also improved, and for making some buffers, because as just now I have told you that what type of salt you are using, whether it is a calcium salt or a sodium salt, which is a typical sodium salt of phosphoric acid, or a dihydrogen salt or a monohydrogen salt, will have a different pKa values, because for 3 protons we can have 3 different pKa values, and depending upon the pKa values and 3 different ranges basically. If we know the 3 different pKa values of the phosphoric acid, we now know that which salt we can use to get a typical buffer at that particular pH. So, 3 pKa values will now control the corresponding buffer range for its buffering action for all these reactions. So, for a textile industry, as for example, if we utilize it for textile industry, and that particular textile industry, if it utilizing some particular buffer medium, so we have to choose that particular sodium salt, which can give rise to the corresponding amount of pH of that particular buffer, which will be useful for your textile industry. So, this particular one as well as this one, the other one, the disodium salt. So, disodium dihydrogen diphosphate. So, if we can have something, that means Na2H2 and the phosphate diphosphate. So, these sort of very complex molecules we can have, but still it is a diphosphate material, and that diphosphate material what we can get is that it can also be utilized as a baking powder. So, in the corresponding baking industries, the baking industry can also utilize this as the corresponding salt. So, unlike our common table salt and all these things, so these are very useful salts starting from leather industry to our food industry. So, food industry always will be very happy in making all these things, but the quality of these salts should be pretty high, because it should be edible in nature, and we utilize this for our eating purpose. We use this and we eat it along with this all this food material. So, this particular one, once we have this, that means when we get this as the sodium dihydrogen phosphate to make it disodium hydrogen phosphate, that means you can go for another level of deprotonation. So another level of deprotonation now what we can use, that the previously what we have seen, that we are going this particular from sodium hydrogen sulfate or sodium bisulfate we are making. We are not using any strong alkali like sodium hydroxide. So second step, so is, as I told you, that is a two-step process. For this two-step process, what we use this now in the for the second step, that means for the getting this as from H2PO4, from H2PO4 how we get HPO4, now you have to use some strong base. That strong base is nothing but your sodium hydroxide. So if we use the sodium hydroxide for this particular purpose, we can get that particular NaHPO4. So all these things, starting from something like your orthophosphoric acid, what we see now, that if we completely remove all the protons from the orthophosphoric acid, we'll end up with orthophosphates like Na3PO4. Na3PO4 is your example for your orthophosphate. Then we can have di and monohydrogen phosphates. That means we can have two hydrogens present in it, that particular salt, or one hydrogen present in that particular salt. It's not only the nature of that particular salt, not only the amount of sodium present with that particular salt, but also the corresponding supply of the proton at a required pK value of the reaction medium, which is also very important. So what we get now, that if we just simply move quickly to some good example of ammonium phosphates, sodium phosphates we have seen, because the ammonium part, the ammonia NH4 plus part is also very useful, as we know, like that of your ammonium nitrate. So ammonium part can be utilized very nicely for your fertilizer purpose to add some micronutrients to your soil. So it's a very simple reaction. Now instead of giving sodium hydroxide or calcium oxide or calcium hydroxide, now we will use directly ammonia ion. So ammonia will be added directly to give you the corresponding monoammonium salt and the diammonium salt like that of your sodium. And they are very much useful. They can use for now fire retarding clothes that we are talking about now, for fire protection, that as additives in fire extinguishing agent for fighting forest fires. That means when you have a huge fire and the huge amount of fire extinguisher are not working, so we all should know what is the corresponding mechanism for the different fire extinguisher nowadays, because even the spraying carbon dioxide can function as a good fire extinguisher. Similarly, large number of, some is foam based, some is other type of base, but we should know also, because even we also don't know, we only see small fire in some building, in some library, in some school or colleges, but we don't know how we have to tackle the corresponding fire in forest, because we don't have much in our country. But in some advanced countries like US and all other cases, their firefighting system is so equipped that they should fight the corresponding fire in the different forests. Because we all know that only a few days back only we see that the California coast and all other things are there, because their wind is also very high speed they are moving. So fire is moving one place to other and the whole forest is getting burnt away. So we should have some special technique for that particular one. So in the fire, in fighting the forest fires, we use this particular ammonium salts for that. Then fire retardant papers, which will not catch fire very quickly. Then textiles, and then polyesters. Then which polyesters? Some polyesters are your polyurethanes. So polyurethanes are there, is one variety. And sometimes to prevent the afterglow in matchsticks, when we burn the matchstick, then sometimes we say that is we extinguishing the fire, your matchstick is glowing. So to retard or to prevent that particular afterglow, because that is dangerous, because sometimes we just extinguish the flame of the matchstick and we throw it away, but still you have the afterglow on the matchstick. So we have to use some material or some chemical for that chemical treatment of that particular purpose, and that chemical treatment is nothing but use of this particular simple ammonium phosphate salts. And this ammonium phosphate salt, so this is not the end of all these things, stories of here, and one of them is therefore is that also if we can able to make is the tetrapotassium diphosphate, which can be used as liquid cleaners due to its high solubility in water. Since it is a tetrapotassium, that means 4 potassium ions are there, no hydrogen, nothing is there. So all the potassium can come out as the potassium ions from that particular salt, and which can be very useful as, because the phosphates will remain in the liquid medium, which can be very useful as a liquid cleaner. So liquid cleaner or liquid cleanser, which can use some other type of salt. So all these salts have very useful application for this particular phosphorus based compounds. Thank you very much.